Are we working? Am I back? Sorry, if there's any first years in here that were watching an hour ago, I'm really sorry. I don't know what happened. Just suddenly there was no internet. And but I've managed to get it back now. I turned it all off and turned it on again. That was my strategy. Yay, hello, you can hear me. Don't know, just went off. It was happening on Friday as well. So I don't know whether it's like the network to the house or what. Don't worry, there was no crisis. There was no crisis at all. Okay. Let's start with some integration. Now I'm going to give you some relatively easy ones, I hope. I'm just choosing a couple. I'm going to give you four. Here you go. I hope it wasn't because I was sharing or something like that. I think it was just the internet. Okay, so we're going to start each lesson with integration because it is the hardest thing and it takes the longest to get used to, and you have to just keep putting. Yeah, sorry, JLo. I don't know what happened there. It just went off and would not do anything, would not come back. At one point, it connected me to the Wi-Fi of a bus that was outside, but I didn't think that was going to be enough to stream. Okay, how long do we think we need for these? 30 seconds each, I reckon 2 minutes. Timer going on. So our target for this 45 minutes is to talk through the A-level specification and make a plan for finishing it this week. Just totally finishing it. 45. Okay. Now, if you have forgotten how to do any of these, feel free to have a look at your notes. So it's not a test. It's more reinforce, and sort of the fourth or fifth time that you see it, that's that bond in your brain between the question and the method of solution starts to come together. $30 more seconds. For those of you who finished, I'm just going to give you one more. Yes, that's right, we have minus cos x. When you differentiate, you get sine. Right. Okay, so rule number one about integration. Ruhab asked a brilliant question there. The question was, does this differentiate to? Always think about differentiating. Try never ever to think about integrating. It's always about differentiating. The main Well, the only ones that you ever actually integrate are sine and cos and sec squared and cosec squared and cosec cot and sec tan and a to the x and e to the x and ln x and x to the n. That's it. Now the next stage down, if it isn't one of those, the next stage down is that you have a look for these really common uses of the chain rule. So we've got something that might be a fraction with something on the bottom, something on the bottom and the derivative on the top. That one's come from ln. Or maybe e to the something and then the derivative of the something. That one's come from e. Or maybe there's two more. Sine of something, and then the derivative of the thing. Or the last one is where you've got a thing to a power and then the derivative of the thing. So all of these are what you get when you differentiate ln of something weird, e to the something weird, sine of something weird, or something weird to the n. All of those, when you differentiate, because you have to use the chain rule, it ends up like this. And then after that, the only other part that there is to integration, if it isn't any of those, you basically have to turn it into one of those. And you've got various strategies for turning it into one of those. You're still going to have to integrate one of those, but we have strategies for getting it there. And the strategies that we have are parts, and substitution, and sort of general trig fiddling, you know, like using trig identities and stuff, general algebraic fiddling, just stuff, specifically maybe partial fractions. That might get them into one of these, or algebraic division, might get it into one of these. And that's about it. That's the integration in a little nutshell. So let's have a look at the examples that we've got here and see where they fit. So sine squared is not in the red list, okay? It's also not any of these structures. So I definitely need one of these blue techniques, one of these either trig type thing or a algebra type thing to get it into one of those 10. And sine squared is just one that hopefully you can just memorize after a while. What we need to do is change it into a half minus a half cos, and then we double the angle. And then once we've done that, then we can integrate it. And when I say integrate, I mean write down what was differentiated. So let's check. What happens when you differentiate a half x? You get a half, yay. What happens when you differentiate sine 2x? Well, you get, it doesn't change the sign. The derivative of sine is cos, so that's good. But then we'd have to multiply by 2. But there's a quarter there, so when I multiply that by 2, that will become a half, and then that's correct. Yes, you can. Yes, you're completely right. What this means is sine x squared. And sometimes it really helps to write it like that, definitely. So the formula that I used here is, this is the formula, sine squared is equal to that. It's a double angle formula. It's the rearrangement of cos 2x equals. So cos 2x is equal to 1 minus 2 sine squared x. If you rearrange that, you get sine squared x is a half 1 minus cos 2x. So it's just a rearrangement of that. And then it's a good question, is it plus a quarter or minus a quarter? So remember, we are only thinking in this direction. We're thinking differentiation. So what would happen if I differentiated this? Well, the derivative of sine is cos. So the derivative of minus a quarter sine 2x is minus a quarter cos 2x. And then the chain rule says we have to multiply by 2. So that is correct there, because the derivative of sine doesn't change it. It's really, really hard if you think in both directions, if you try to think integrating as well as thinking differentiating, gets so confusing with the minus signs. Whereas if you only ever differentiate, it's much, much simpler. Sine goes to cos, cos goes to minus sine. Now, Rehab makes a really good point, which is, if we write it like, I'm just going to attempt the rubber here, even though I know it doesn't like it. If we write it as suggested by, I can't remember who, like this, then wouldn't that make us think that it was sine cubed x with a third at the front? So the 3 comes down, cancels with the third, and then we change it to sine squared. Good. And then chain rule, and then we multiply by the derivative of the inside. So if I differentiate this, what I get is 1/3 sine cubed x times the derivative of sine x, which is cos x, and that bit is there because of the chain rule. So that would be wrong, because if you differentiate that, you don't get that. So this is one to just learn, okay? There are 4 that you just literally memorize. Sine squared, cos squared, tan squared, cot squared. So all 6 of the trig squareds, all 6 you can do. You can integrate sine sec squared, because it's just tan. You can integrate cosec squared, because it's just minus cot. You know what got differentiated. They're here, look, they're in our list, sec squared and cosec squared. And then the other 4, sine squared, cos squared, cot squared, tan squared, all of those 4 always use the same formulas. So I'll write them down, because these 4, and that's why I keep chucking them in, because these 4 you really do have to actually be able to just do. So if you've got to integrate sine squared x, you change it to 1/2 minus 1/2 cos 2x. If you've got to integrate cos squared x, you change it to 1/2 plus 1/2 cos 2x. If you've got to integrate tan squared x, you change it to sec squared x minus 1. And if you've got to integrate cot squared x, you change it to cosec squared x minus 1. Just learn those. Just memorize them. Yeah, magic hexagon gives you these 2. And these 2 come from the double angle formula for cos. Literally just rearranged. Yeah, it does sound like voodoo magic, you're right. Okay, so what about this one, cot? None of these are cot, so I can't just write down the answer. It isn't this or this or this or this. It isn't like trig of something and then its derivative. It's not any of them. Katie, if you think about differentiation, so if I write down if I write down minus 1/4 sine 2x, what's the derivative of that? This is the question. What is the derivative? Now, the derivative of sine 2x is cos 2x times 2. Exactly. Well, except for it would have a minus 1/4 at the front still, wouldn't it? It would be like that. So the minus 1/4 is still sitting there. Then you've got the derivative of sine 2x, which is cos 2x times 2. So that comes out to be minus 1/2 cos 2x, which is what we wanted. We wanted the minus. Times 2 is because of the chain rule. So the derivative says, the chain rule says if that's not an x, you multiply by the derivative of the inside. That's what the chain rule said. And I'll reiterate in case you didn't see this before, that the chain rule, if you use the chain rule by writing u equals da 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 da, and then doing dy by du by dx, and then timesing them, this will be really hard. Integration will be really hard. Whereas if you can think of the chain rule just literally as and then multiply by the derivative of the inside, then it will be much, much simpler. Good. Well done, Katie. And well done for keep asking. It's really hard. It's really the easiest thing in maths is to just go, oh, yeah, okay, whatever, yeah. It's minus whatever. And it's really hard to keep admitting to yourself that it doesn't make sense. So you did well there. Okay, cot. This is another little trick, really. Cot doesn't, it's not a trick, but cot isn't any of these. So we need to do something. It isn't any of these, except for that it is. It is because this one. It's this one here. And the fact that I've written cot, same thing with tan, it makes it disguised. But if I rewrite this, if I get rid of that cot there, and instead of cot, I write cos x over sine x. Now that is cot. And now what we're looking at, it still isn't any of these. That's our aim really, is for it to be one of these, but it is that one. It's a fraction and the bottom differentiated is the top, which means that the answer is ln. Now notice I always just leave a little gap whenever I integrate anything. Integrate, there's no such thing as integrating. When I write down the answer, when I write down, good Daniel, yes. When I write down what was differentiated, I always leave a little gap in case I need to do any adjustment. So there's my basic answer. And then I think, right, how does that differentiate? Let's think this through. Ln of sine x differentiates to 1 over sine x. Then the chain rule says I have to multiply by the derivative of sine x, which is cos x. Brilliant, done. Don't even need anything at the front. Okay, so that's that one done. Right, now the one below I'll do next, tan squared, because I've already told you how to do that one. Tan squared is just a classic, change it to sec squared minus 1. Okay, what was differentiated? Tan was differentiated. Because tan, when it's differentiated, produces sec squared. So if sec squared has been produced, it must have come from tan. Yep, and then minus x, done. Done, done, done. Now, this one. Is it any of those? No, 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 no. It's not any of those. Oh, no, I didn't mean to write ln x there. I meant to write the derivative of ln x, which is 1 over x. So it's not any of those. No, 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 no. That's annoying. Okay, it's a fraction. Is the derivative of the bottom on the top? No, annoying. So this narrows it down. These are the sort of processes to think through. I've narrowed it down to, I either need to use partial fractions or algebraic division or just basic algebra to fiddle around with it. Don't go anywhere near substitution parts or, well, it's obviously nothing to do with trig. So you're just looking at it and going, can I muck about with this? Now the bottom, yes, Isabel, it is stats and mechanics overview, but we always start with integration, always. Because our integration takes so long to get hard at. To get hard at, to get good at, because it's hard. Right, it's not partial fractions. There aren't two things on the bottom to pull it apart. Yeah, algebraic division, algebraic division. Now I'm going to show you my little trick. And you can choose, because I did this the other day and I did it quite fast and some people were saying, well, wait, what did you do? So I'm going to show you both ways and you can see which one you like. The way that I do it is a sneaky little trick. I write it like this. Instead of x add 1 on the top, put x minus 4. Now, obviously that so far is a lie because it was meant to be x plus 1, not x minus 4. But I want x minus 4 so that I can create this V shape like this. And then I can write it as x minus 4 over x minus 4, which is 1, and then something else. Now I have to make the top true. So instead of x add 1, I can't write x minus 4 unless I then put plus 5. And that's what gives me the other bit. It's a cute little trick. And now I can just integrate. Done. Yes, Daniel, we could have written it like that. We could write x add 1 over x minus 4 equals x over x minus 4 add 1 over x minus 4. We absolutely could do that. But the thing is, we are specifically trying to create either one of these or one of these. that's what we're doing. If we don't end up with a red one or a green one, there was no point in doing whatever we did, because we can only ever integrate the red ones and the green ones. That's it. The only thing with the green one, that sign, it could be a different trig function. It could be cos or sec squared or cosec squared or cosec cos sec tan. It doesn't have to be sine, but we're trying to get towards that. And this guy I can integrate. That's come from ln x minus 4, but this guy is the exact same problem I had a minute ago. The derivative of the bottom is not on the top, etc., etc. You know, it doesn't work. It's true, but it doesn't help me. What I did here was I created the bottom on the top and then made an adjustment so that that was true. It's a cool little trick. I'll show you the other way of doing it with synthetic division. So on the top, I've got x add 1. One lot of x and one lot of 1. I'm dividing by x minus 4. So the thing that would make that 0 is 4. You know, like factor theorem, the thing you would feed in to show that it's a factor is 4. So the 4, the thing that makes the bottom 0, that goes there. All you do is whatever's there, copy it, and then multiply these two together, multiply this guy and this guy together and put it there. 4 times 1 is 4, and then add them up. And then this 1 here is that 1 there, and this 5 here is this 5 here. So it's the same way. You could use, yep. Only works, Ibrahim, you're quite right. It only works for a linear divisor, but new spec, you're only getting linear divisors. So it's fine because you won't get a quadratic divisor because the new spec specifies that you will only get a linear divisor. Okay, now the last two. And yeah, integration, you're completely right. Integration is hard and it takes a long time to get good at, and that's why we're doing it literally every single day. So which ones have we seen so far? We've seen the sine squared and the tan squared. We've seen one where we needed to do a sort of algebraic division-y type thing. I'm not going to do a partial fractions one because they, you know, partial fractions just take so long, but they exist. And now we'll look at these two. Right, how am I going to do these two? These were the hardest ones. Any clues? Anyone know? They're not the 10, for sure. They're not the red ones. So are either of them the green ones, or do I need to go into parts or substitution or using trig identities? What do I need to do? Integration by parts, substitution, parts, lots of parts, derivative in front. So the derivative, which one of these then do I not need? There's one of these that I don't need parts for. Do not need parts. And I put it there deliberately to emphasize this thing, that we actually only need parts in a very few situations. Very few situations. Yeah, the first one, second one, first one, second one. Right, the first one I do not need parts. The second one I do need parts. How is that? What is the difference? How are you supposed to look at a product like this times this and a product this times this and know which one's parts and which one isn't? Well, it's to do with the green ones. Are either of these the green ones? Okay, let's have a look. We have got sine of a thing multiplied by the derivative of the thing. No, that is not the derivative of this. No. What about here? We've got e to the thing, and then the derivative of that thing at the front. Yes. The derivative of 3x squared is 6x. Fine, there's no 6 there. I can deal with the 6. That's fine. This one is not parts. It would work by parts, but it would take a million times longer. So I will quickly show you both approaches. One of them, approach number 1, is to recognize it as one of your green ones and just say, well, I know what got differentiated. That got differentiated. The derivative of e to the 3x squared is e to the 3x squared. Then the chain rule says multiply by the derivative of the 3x squared, which is 6x. I want the x, I don't want the 6. Stick a 6 in front, that's the end. Lovely. Now, this is what happens when you try to use parts. Okay, u is x, the derivative of u is 1. The derivative of v is e to the 3x squared. V is O. How am I supposed to integrate e to the 3x squared? This is what a lot of students will do. No, does not work, because look in the other direction. So let's say I differentiate this guy. If I differentiate this guy, there's a chain rule, exactly a chain rule. So if I differentiate this guy, then I'd get e to the 3x squared. Then I'd have to multiply by the derivative of the 3x squared, which is 6x. So I would not get this. I would not get that. You can't integrate this. So the whole of trying to use parts completely breaks down. It just doesn't work. Okay. The derivative of e to the x is e to the x. The derivative of e to the thing is e to the thing times the derivative of the thing. That is literally what the chain rule tells you to do. It says if it isn't just an x, then proceed as normal, but then times by the derivative of the thing. You can integrate it, but it's not expected at A level. How would you integrate e to the 3x squared? I'll tell you where. How would you integrate e to the 3x squared? You know this graph that you should know, the normal distribution graph. You know when you put it in your calculator and you say what's the area to the left of this, for example, when you're doing normal distribution, that is an integral. It's the integral of this curve, right? But this curve has got a very difficult equation. It's something like 1 over the square root of 2 pi e to the minus 1 over 2 pi t squared, I think it is, something like that. And that is ridiculously difficult. There isn't an analytic solution to it. You can do it using the trapezium rule and get loads of approximations, which is what your calculator is doing, but you can't just integrate it. In fact, I think you can't integrate it analytically. So I think it's not just that it's really hard. I'm pretty sure that that one, e to the 3x squared, is one that cannot be integrated. But let's think this through. I think this is important to give this the time. So parts does not work. Another question was, why isn't it a 6x? So let's write that one down. 1/6 x e to the 3x squared. So how do we differentiate? Only ever think about differentiating. So how would we differentiate that? Well, it's a product. So we would hold still one of them, then differentiate the other one, and then a plus, and then we would hold still the e to the 3x squared and differentiate the 1/6 x. Is that the same as that? No. Therefore, that is not what was differentiated. It's the differentiation skills that really matter. Now, the big difference between this one here and this one here is that the derivative of the thing inside, or the thing up there, the thing within the e function, its derivative is there. Whereas we don't have that here. We've got an x at the front and then sine 2x. So this is one of the 3 situations where we need parts. There are only 3 situations where we need parts. So we need parts if, let's get rid of that and write it down. We need parts in the following situations. Situation 1 is where there's a learn. Okay, if there's a learn, you need parts. Situation 2 is that you've got stuff to do with X, and then you've got E to the stuff to do with X. Situation 3 is that you've got stuff to do with X, and then I'll use sine as an example, but it's sine or sec squared or cos or cosec squared, something you can integrate of stuff. This is other stuff, not the same stuff. They're the only times we need parts. So we don't need parts for this one, but we do need parts for this one. U is X, U prime is 1. Then across the bottom, V prime is sine 2X. Now, try not to integrate. Try to differentiate. Try to differentiate down. So look at that gap and think, what would I put there so that if I differentiate it, I get sine 2X? Okay, excellent, Katie. It's cos 2X, but not quite right yet, because if I differentiate cos 2X, I get minus sine 2X. And also the chain rule says I then have to multiply by 2, and I don't want the minus and I don't want the 2, so I put a minus a half at the front there. And then this is how I remember the integration by parts formula, like this. So when you're choosing and when you're building it up, what you're doing is going like down here, differentiating, then across there and write this one down, write that one down, differentiate it, go across there, write that one down. And then you are going up, but really you're not, really you're going down because you're thinking about differentiation rather than thinking about integration. And then the formula is the 2 times together at the top minus the integral of the diagonal line. And sometimes it really helps to pull those numbers out the front. Just a bit of a mess having it in there. Look, that's much nicer. And then we're done. Right, plus or minus. I'm going to leave a little gap there for you to have a think about what goes here. Just give you about 15 seconds. Excellent. What got differentiated? Always what got differentiated. Right, that is our introductory integration for the day. And the reason that we are doing that is that it's a hugely important part of the pure syllabus, hugely important. So in the pure syllabus, why are you not going back a page? There we go. In the pure syllabus, actually will write this out. I know we're doing the stats and mechanics today, but just to remind you, we've got trig and differentiation and algebra, and all of that equals integration. Because every single integral is what did I differentiate? So you need to be good at this, especially the chain rule. And loads of those integrals, you need to use a trig thing to rearrange it. So particularly sine squared, cos squared, tan squared, cot squared, but also other things that you might need to use a trig identity. So you really need to know your trig and be good at your trig. You need to be able to differentiate. And also the algebraic brings in loads of the algebra stuff. Maybe you've got like partial fractions, maybe you've got algebraic fractions, maybe you've got like, maybe you've done a substitution and then it gives you u plus 1 all over root u. You need to be able to do that. So all of these things feed in. So by focusing on the integration, not only do we make progress with a difficult topic, but we also are constantly using all these other skills from the most important parts of the course. So that's why it's so important. Okay, stats and mechanics. Here it is. Here is the outline. I'm going to tell you how many marks this is worth, each of these, in your final exam. on average, right? It's usually the same amount roughly. So in your exam, if you go up by 10%, you go up a whole grade, right? That's more or less what a grade is. The grade boundaries more or less go up in 10% jumps. Sometimes it's a little bit different, but ish 10%. Now, if you could only do one topic in mechanics, the VT SUVAT projectiles is the one to do. This is worth by far the most marks. This is worth 8% of the whole thing. Okay. Oh, yeah. Ibrahim saying you can't technically integrate e to the x squared, but you can use a special error function. What the error function does is it doesn't integrate e to the x squared. It's a bit like when you use the binomial expansion and you only use like it up to the cubic term or something like that. And what you do is instead of only taking the beginning of the expansion, because e can be written as an infinite expansion, and instead of taking, well, you can't take all infinitely many, but instead of taking just a few and then going, oh, the rest is probably small, you actually write down what the rest would look like. And that gives you an idea of how much you will be wrong by. So that's what an error function is. It's on the end of the integral. We kind of take it out of the integration process and put it on the end to allow us to estimate errors. That is correct. That is what you do. No, Ibrahim hasn't done A-levels before. Okay, so 8% of the whole A-level. Okay, almost a whole grade. Compared with moments. Now, think about how much work you would need to put in order to get really, really good at SUVAT and projectiles. Okay, think about that. Now think about how much work you would have to put in to get really, really good at moments. A lot more work. If I gave you 1/2 day and then I tested you on a whole A-level paper, and you chose to spend that day on moments because you didn't really learn moments, it was put to the end, your teacher set you work on it, but you don't really get it. You would spend that time on moments because moments, you know, is missing from your syllabus. Then you would do the paper, and do you know how much you could go up by maximum? This is how much more you would get. 2%. All of that work, learning a new topic, practicing it, it's really difficult, getting good at it, trying it again, it takes ages. And if you succeed and you go up and you get moments completely sorted, then your grade will go up by 2%. Whereas if you get SUVAT and projectiles sorted, your grade would go up by 8%. If you get connected particles sorted and the F equals ma with all the forces on, and then using F equals ma in those two directions, then your grade will go up by 5%. Okay. This is on average. So it's on average, but also don't forget that say your moments question is out of 9, which is quite a lot for a moments question to be out of 9. If it was out of 9, then the whole paper is out of 300. So 9 divided by 300 is 3%. So even a big moments question that's 9 marks, that's actually 3% of your A-level, of the whole A-level. The big 4 are these ones in the middle. So you can get, this is worth about 4%, this is worth about 4% of the whole A-level. So if you could do those 4, just the red ones, and you didn't worry about literally anything else, then you could get 21% of your A-level from the stats and the mechanics. Okay, just the red ones. Now, 2/3 of the A-level, 67%, is on the pure. So let's say you do quite well in the pure. Let's say you're not going to get 100. So like, say you get most of those marks, most of that 67%, which is what the pure maths is. So let's say on the pure maths, you get, I don't know, like say out of 200, you drop 50 marks, 150 out of 200 would be 75%. Boom, A star. A star. Okay. Now, how much work would you have to put in to make your vectors better? That's how much you'd go up by. Probability, 3%. Correlation, 2%. Sampling rounds to 0. It literally is basically worth maximum 1%, but it's actually less than 1%. Data is 1%-ish. Variable acceleration, 2%. Okay. And when we look next, when we start going through the papers, the whole point of the TT method, well, not the whole point, but part of the fundamental part of the design of the method is that the work you put in is proportional to the marks you will gain by doing that work. And it's a really, really important reason not to learn topic by topic, because if you learn topic by topic, you will end up putting a lot more time into something that even if you crack it and become an expert, will only make you go up a tiny little bit. So the revision structure that we use in TT and the learning structures that we use, it's all about getting the most possible marks for the work that you put in. So if we're going to do anything, we need to make sure that the VT and the SUVAT, binomial normal, and the connected particles are fine. We can then work on the other ones as like a funsy, definitely, but they're not worth really, really loads of time. So this week, I'm going to concentrate on those 4. And that's why in the schedule, you will see that we have got those 4 and not the other ones. So if you want to have a look at this schedule and fill in the gaps, I think it would be a good idea over this week. The target for this week is that we are going to finish the A level, finish it, okay, totally finish it. So this is all of the notes. If you want to make proper notes using the notes templates and stuff so that they all look the same and they're all organized, then what I would suggest that you do is come along to the lesson tomorrow, well, all of this week, and we will do normal distribution, all of hypothesis testing, moments, and friction. Now, the reason I've put moments in there instead of projectiles is because I know a lot of people haven't done it, but I'm open to discussion on that one, because I ummed and ahed for ages about whether or not to put in moments or projectiles and SUVAT. What do you think? What would you prefer, especially now that I've shown you how many marks you're going to get? Yeah, large data set, 1%. 1%. And if you think how many marks you're going to drop because of making mistakes. So if you took all of that time away from the large data set and put it into your FFS journal and really thinking about those mistakes and focusing on them and analyzing them and really looking at your FFS journal before you do a paper, you will go up by 10%. And even if you memorize the large data set and did all of the past paper questions ever, and you were lucky with the way that you write, that you use the right words, then, ooh, 1. No, it rounds to 0, to be honest, the amount of marks you get. Projectiles. Okay, projectiles, cool. Let's do that then. Yeah, let's do projectiles then. Forget it, forget the large data set, really doesn't matter. Okay, I broke a rule, didn't I? Oh, I did put a timer on, we've got 4 minutes left. I thought that I didn't. Okay, so to finish off for today, really, I want to set you off on your week, on your journey to the end of A-level maths, okay? I want you to, today, if possible, make a recce of everything you need to do. So you can go through the pure map from last week and the applied map from this week, and just go through and tick off, so like these ones, and go through and tick off. Maybe you're not brilliant at it, but you've learned it. Okay, you don't even need to have notes on it, just you've learned it, so that if I then showed you how to do a question, I would be using things that you do know. So that sort of level of knowledge, not it's amazing, I can do it, I've done all the questions in the book, not I've got a page of A4 of notes on it, although you could do that if you want. So you could do individual lessons on any of these things, or don't forget in the course you've got the revision notes and you can watch them. Each of those is about half an hour filling in one side of A4 that's got everything that you need on it. So they're the ones that look like this, okay? So each topic, one side of A4, everything you need to know for that topic. So that might be a better way of doing it, to fill those in so that you know you've got everything. Now, I'm going to be working with you to support that process all the way through this week. So I'm going to be checking in with you at the beginning. How many have you got left? How much do you want to do today? How much do you want to do tomorrow? And then we're going to try to get that to the point where next week, this time next week, everyone's ready to do a paper in test conditions. Okay, and you don't need to do brilliant on it. We're going to make solid progress. So that's the plan for the week. What do you think? Yeah, moments is not easy. Moments is not easy, but yes, I will do the same for pure. Yeah, I will tell you what each percentage is worth, definitely. But you don't forget that the way that I structured it on the page, the red ones are worth the most, and then the green ones, and then the blue ones. So you've got an idea already. Okay, you're excited. Good. I really like, I really like finishing a course. For me, it's the best bit. Like slugging through the course is kind of frustrating, but when you actually finish it and you're like, okay, it's done. So final thing, a couple of people asking about what we're going to do this week and what we're going to do next week and where the revision things are. The course map, this is your exambulance. The course maps are in there. The revision notes are in there. And the progress chart you don't need till next week. Oops, I accidentally clicked on maps. So there's the maps. The study schedule shows that what we're going to do this week is focus on particular topics. So tomorrow we are going to be focusing on the normal distribution here. So I'm going to go through some key questions with you that more or less show everything that you need to do, all of the techniques. It'll show how important it is to draw a diagram, how you can use the symmetry of the graph in different situations. But the only thing I won't do from the normal distribution is the hypothesis testing. Then the next day, Wednesday, we'll do all of the hypothesis testing. So that's binomial and normal and correlation. They're the three types of hypothesis tests that you might get. Then on Thursday, I'm going to change that moments to projectiles because it's worth so much more. So we'll focus on projectiles. And again, what I'll do is come up with sort of 3 questions. Yay, good timing. 3 questions that basically cover everything so that you can see how the knowledge is applied and then you can take that into your practice. And then the reason I'm going to focus on friction particularly, it is a focus on friction, but it's going to be general connected particles type problems. I'm going to try to make all of those connected particles have something to do with friction so that we can get that kind of sorted of which direction the friction goes in, how the friction changes direction under certain circumstances. And then if that modeling is set up properly, then it's just first year stuff from that point. So neither understanding friction, being able to resolve forces is the only thing we need to add to what you did in the first year in order to make it second year. So that's the plan for this week. Your homework for today, if you would like to do it, is to use the maps to make a list of the topics that you still want to make notes on, divide it by the rest of this week, and then stick to your own schedule so that next week we can start doing work in test conditions and working on the TT method. Ruhab and Raseb, don't worry about the next week. You'll see it come together as it comes together next week, okay? Lovely to see you all. As always, a million billion thank yous to you for turning up and for trusting me with this hour of your time. And I really hope that what we've been doing with the exambulance is helping you to build some confidence and get yourself sorted. And you know, if you're pleased with your result that you get next month after, is it April yet? then great. If not, you are going to be in the best possible position to smash the exams and stick 2 fingers up to whoever it was that said you were only going to get a whatever. Okay, I'll see you tomorrow. My study with me's, by the way, are now going into the course for subscribers only. So I'm afraid the study with me is going to be inside the course, not on YouTube. But there are still those other study with me's on YouTube, so you could just watch those and use it as an opportunity to do some study at the same time if you wanted. So I might see you at 4 o'clock in the course. Bye.